In this problem, we're looking at a 5-kilogram watermelon that's dropped from a third-story balcony 11 meters above the street. However, the water department forgot to replace the cover of a manhole, and so the watermelon actually falls into a 3-meter deep hole underneath the street. How fast is the watermelon going when it hits bottom? So in this situation, to understand what's going on, we have the building, we have our balcony, our watermelon is going to fall downwards, but it's not just going to fall down and hit the street, it's actually going to fall into a manhole cover and fall an extra 3 feet at the bottom. And eventually it's going to hit at the bottom of that manhole. And so in this situation, we're looking at the motion of an object, and that object is subject only to gravity. There's no other external forces in the system, and so this is a great candidate for us to use a conservation of energy, to use the conversion of energy between kinetic and potential sources. So in order to do that, we're going to look at the energies that we have. So this is our conservation of energy. We're looking at all the different types of energy in this sort of system. There's no external forces that we have to consider. Looking at this situation where we're dropping a watermelon, where it's falling down, there's no springs involved, so we can go ahead and discard spring potential energy. The watermelon is flying through the air the whole time. We can presume that we're neglecting air resistance, since watermelons aren't that big and it's not moving very quickly. And so we'll throw out any sort of thermal energy change there. And so we're looking at the kinetic and potential and gravitational potential energy at the beginning, and kinetic and gravitational potential energy at the end. Since we're moving up and down, we do have to consider this gravitational potential energy. And whenever you have gravitational potential energy, you do need to have a reference height from which you measure all the other heights for your gravitational potential. Now, I typically like to put my reference height at the very bottom, and so then all of the gravitational potentials are positive relative to that lowest reference gravitational potential. But here it seems more natural to measure the gravitational potential from ground level, since all of the heights are measured relative to ground level. So we're going to do that here to see how that will behave differently, and yet how we'll get the exact same answer regardless of what arbitrary reference point we pick. We also know that the initial kinetic energy is 0, since we're told the watermelon is dropped from the third-story balcony. So we can assume from that the initial kinetic energy is 0, since dropped means it's not given an initial velocity. In this situation, we can rewrite our conservation of energy then as the gravitational potential energy at the beginning, and then the kinetic energy and the gravitational potential energy at the end. We're given the mass of the watermelon, but we notice, as this happens quite often, there's a constant factor of mass in our equation, so we don't actually need to know what the mass of the object is. We're told that we're initially 11 meters above the street, so that's our initial gravitational potential energy. We don't know the velocity when we hit the ground. That's what we want to find. And at the end, when the watermelon is hitting the ground, we are 3 meters deep. We're 3 meters under the street. And so in that situation, that 3 meters deep is below our gravitational potential, and thus has to show up in our equation as a negative amount. when we want to solve for the velocity, we'll have to move this term over, and we see that we're going to get a combination of those two terms. And in fact, you could rewrite this as 9.8 times 14, where 14 here is the total distance dropped by the watermelon. So it doesn't matter if you treat it as from 11 meters above the reference to 3 meters below, or a total drop of 14 meters. You're ending up with the same value right there. So here, VF squared is 274.4, and our velocity hitting the ground is 16.6 meters per second. Technically, this velocity is downward, but we're asked how fast. Typically, that's looking for a speed, an amount, and not necessarily direction, and so we can report our 16.6 meters per second as the magnitude of our velocity.